All right. So I think this is our lecture 4 on the 24th of November. We are still looking at the analysis of a structure in terms of finding its slopes and deflections using the moment area method. Okay. So I think last week, so let's just do a recap of last week's lecture. So I think with last week we formulated two equations or two theorems, all right, based on the moment area method. Okay. So what's happened to my pen? Okay. So with a recap, so we mentioned that when looking at the moment area method, if we have the beam, all right, so with the beam, we take into consideration the elastic curve of the particular beam, okay? Then with the elastic curve, we look at the rotations at different points along the beam, all right? So that if this beam AB, at any point along the beam, will have some rotations and also some deflections, all right? So for example, if we take point C, which is some distance on the span, so if this is C, once the beam deflects, this becomes the new point of C. So let me call it C prime, okay, just for emphasis sake. So this new point of C on the elastic curve would have undergone some deformations, okay? So here, it was initially straight, now it deforms, so it's part of the curve of the beam. So now this deflection delta C, we need to find that deflection. And also we need to find, if we draw a tangent to the point on the elastic curve, okay. So the angle the tangent makes with the horizontal line is the theta C. Okay. All right. So we need to find these respective deformations with respect to the point C on the elastic curve. Okay. All right. So yeah, so Daniel, thanks for the reminder. I'll talk to the class about it later. Okay. So with this, it means that at every point, so we can find different points. We can find point K, point M, even the point B, point A. So at these different locations, we can determine their respective deformations and their respective rotations or slopes. All right. And we can do that using the moment area method. Okay. But with the moment area method, it's defined in such a way that you cannot generally find the deformations and rotations of the points as it is. All right. You need to find them with respect to other points. Okay. And that's how can we have the two theorems. And the first theorem talks about, so the first theorem looks at slope. All right. And typically slope between points. Okay. Or the tangent of points on elastic curve. So it's not a slope at a particular location with respect to the horizontal, but it's a slope between 2 points or two tangent points. Okay. So sorry. So the slope between 2 points, so any 2 points of interest to us, right? So it could be between points C and K, points K and M, points B and A, whatever point we are looking at. All right. So the slope between 2 points, or the change in the slope between 2 points, let's say, maybe let me still maybe use theta BA. So theta B is the slope between the 2 points B and A, all right, or the tangent of the 2 points, or where the 2 tangents of the point intersect. So that change in slope is pretty much the slope between those 2 points. And we say that it is pretty much what the area of the M over EI diagram. Okay, so the area of the M over EI diagram. Okay, so for example, going back to this, going back to the elastic curve. So here is the tangent drawn at C. Okay. Now let me draw another tangent with respect to M. Okay, or a tangent passing through M. What color would do? So let me just draw. This is going to look a bit funny. Okay. All right. So this is a tangent passing through M on the elastic curve. All right. So let me answer this question before I move on. So someone wants to know if during exams or during whatever, in a quiz or whatever, you would be required to use a specific method to solve the problem. And the answer is yes. All right. So, for example, if I give you a cantilever beam to find its deflection at certain points, I would specify the kind of method to use to apply. All right. The reason is that I need to know if you have a good understanding of that method. I mean, these are for examination sake. Okay. Out there in the world, when you start practicing or you want to do a bit of calculations, you are allowed to use any method you are comfortable with. All right. But for exam sake, whether it's quiz, assignments, midterm, main exams, you would be given or you would be required to use a specific method for whatever question you are looking at. Okay. All right. So now I have the tangent memory aid. Will you be given memory aid? It depends on the method, because a method like the moment area method, there are two theorems. The first theorem has to do with slope between points, and then the second theorem has to do with the vertical deviation between between a point on the elastic curve and then a tangent drawn from another point. All right, so that the vertical deviation here is equal to the moment of the M over EI diagram. Okay, maybe this, let me just put this one here. Okay, so this is the equation. This, I don't think you would require a memory aid for these theorems. All right, they are just two. Depending on what the topic might be, some topics will have some bit of a little bit more complex set of equations. So yes, maybe those ones you might be given some memory aids, but I mean, with respect to the moment area method, where there are only two theorems, which are easy to memorize and also easy to write them out. In most cases, you might be asked to write them out. So you really need to be given a memory aid to that effect. I hope I've answered all the questions. Okay, so let's go back. So with the first theorem, so now I have these two tangents, tangent M and then tangent C. Okay, so they intersect. Let me just take this guy away. They intersect at this point right here. The two tangents intersect. So the angle between the two tangents, this angle theta, per the moment area method, the first theorem definition, the change in slope between these 2 points, so between point M and C, that angle here is theta MC. And theta MC is simply the area of the moment diagram between those 2 points. Okay, so here you have the elastic curve. Okay. assuming I'm just going to assume the moment area diagram. It could be any diagram depending on what loads you have on a structure. So assuming that maybe this is your moment, your bending moment diagram, from what I'm drawing, it might look like this. So if this is your moment area diagram, this point here is C, and maybe this point here is M. All right, I mean, in terms of where they're located on the structure. Okay, so with the slope is simply the area or the slope theta MC or CM is the area between these 2 points. All right, so that's generally what the uh, moment area method is with respect to slopes at different points. Okay. Now, to find the vertical deviation is not always, or typically, it's not the actual deflection of the point, right? It is just the how far a tangent drawn from a point is to another point on the elastic curve. All right. So for example, I have point M. So I have point M on the elastic curve. All right. So when I draw the tangent passing through C, which it's shown with the yellow highlights. Okay. The vertical distance from the point M on the elastic curve to the tangents at C. So that vertical, let me see if I can find another color. I'm running out of color choices. Okay. So this vertical deviation, this vertical measurement here, okay, we call it TMC. Okay, TMC, and TMC is simply, or some will say delta MC, right? It's pretty much the same thing. All right. And it's important that with the vertical deviation, the way we write them, I mean, we write the subscript is very important. Okay. The first subscript indicates the point on the elastic curve. And then the second subscript indicates the deviation of that particular tangent, or the tangents that we are looking at with respect to that point, okay, on elastic curve. And since the second theorem requires us to find the moment of the M over AI diagram, it means that we need to know about what point we want to take the moment. Okay. And we take the moment about the first subscript, which will be M. So in this case, again, you find the area of this diagram, and you find the corresponding. So assuming that this is the its centroid might be somewhere here. Okay. So we take the moment will be from the centroid of the region that has been shaded to M. So this becomes your X bar. Okay. Your X bar is not to C, but it's to M. That is if you want to find TMC. In the same way, we can also look at point C on the elastic curve, which is right here. Point C on the elastic curve, its vertical deviation with respect to tangents, tangent drawn from M, this vertical deviation here is TCM, okay, or delta CM, okay. So with TCM, the same idea, it is the area between point C and point M. But this time around, the moment is taken about C, not about M. So going back, if I rewrite this here, this X bar would be valid if you are looking at TCM. Sometimes TCM can be equal to TMC. Sometimes, but it's hardly the case. So I can say that generally, TMC is not equal to TCM. Generally. All right. Yeah, there are some instances that you can have that happening, but mostly they are not the same. Okay. So once you find these slopes, theta MC or theta CM, with this case, they'll be the same. Yes, so, oh, sorry, I didn't bring my I. This is M over EI. So it's always the M over EI diagram, okay? So you have to divide. So once you find the moment, the bending moment diagram, you need to divide that by EI, by the EI. Okay. So it means that you need to understand how to draw bending moment diagrams. Okay. I think next week you guys should meet for tutorial session. All right. So let me know the day you want to meet the TAs and let's plan with it. So at least you can start solving some questions on how to draw bending moment diagrams. Okay. Your second assignment should be coming in by the close of today. And usually assignments are due within a week. All right. Yeah, I think within a week is fine. So let's have that in mind. Okay. So this is generally what happens with respect to the theorems. And you could see that these might not give us the deflections of these points, right? So going back to our what's the name? Going back to our elastic curve, the actual deformation of M is here. So this is delta M, and I already have delta C. Okay, so in most cases, delta MC is not equal to delta M in most cases. So again, generally or usually, delta MC is not the same as delta M. So here you need to apply geometry to be able to use this information to get delta M. Okay. And that's where it becomes a bit challenging using the geometry. Finding TMC, theta MC, TMK, theta MK, whatever it is, those are pretty, I won't call them easy, but then they are less challenging, right? It's when you have to apply a bit of geometry, a bit of trigonometry to be able to find the deflections or the slopes of the different points, then that's when it becomes a bit challenging. And one of the best ways to overcome this challenge is to be able to practice, like look at different scenarios, be able to understand how these things work, and then you should be good to go. Okay, just give me a second. Let me see. Okay, hopefully. When you're sending me messages, please send it to the other participant that says send questions here. Okay, so that I can see on the second screen as I do this. All right. Yeah. So we can look at what we are doing last week and then move on from there. Great. So last week we had this example which I mentioned that, no, I think it's the one below. Yeah, this one. This can be found in the Hibla, I think, yeah. Which edition is that? App Shop from the 5th edition upwards. The examples are pretty much the same. All right. I should have also posted that example. I mean, like posted a snippet of it on the V campus as well. So you can always check it. Okay. So we have a simply supported B. Okay. AB, that two key points on the beam, point C anywhere on the beam, and then point D. And point D is where the load is applied. Okay. From here, we are asked to find the slope at C. All right. So the slope at C is the angle the tangent at C makes with the horizontal. Okay. So if I draw this as my tangent at C, or tangent passing through point C, that's actually the proper way to say it, the tangent passing through point C. So if somewhere on the tangent line is C, when you draw a horizontal line passing through that point C, the angle the horizontal line subtends with the tangent passing through C is called theta C. Again, the theorem will not give you, or the theorems for the moment area methods are not theorems to find C. You need to find angle between points, angles between points. That's what the theorem states, at least the first theorem, and the same also with the second theorem. All right. So drawing the elastic curve is just pretty much drawing the deflected shape. Okay. If you have a beam with a point load applied somewhere along the span of the beam, definitely the beam is going to deflect downwards. At least in this case, where you have only one point load, the beam will deflect downwards. So you always have this shape, deflected shape. All right. Okay. It's important. And that's what I have drawn right here. This deflected shape. I should have I think I should have a hand. Oh. So I think it's around the other one that has it, not this guy. Okay. So, okay. All right. So that's what I'm going through. I'm going through the example we started last week. So maybe if I get to that point, I'll explain this whole A and B thing for the trapezium. Okay. So the goal is that we need to find theta C. All right. But before we can find theta C, we need to find other data sets or other values, which then can help us to find the theta C. Okay. So here I draw two tangents passing through 2 points. So the tangent C passing through point C, which is the purple, I think, purple, violet, whichever color choice we want to say. Then also, so let me call this tangent. Oops. So this is the tangent passing through C with the yellow highlight. Okay, now I've changed its color. Okay. Then we have another tangent passing through A, again with the cyan, whatever color highlight. So these are the two important tangents to us. All right. So I came up with this approach that, okay, if this is my line AB or my beam in its initial position AB, and I'm able to draw a tangent passing through A. All right. And then I know that A and B are points at the supports, which means that they will not undergo any deflections, right? Generally, they will not undergo any deflections, okay? Which means that the point at B will still be at where it is on the elastic curve. I can find this distance, this vertical deviation, which is TBA. So if I find TBA, and I know the length of the line, I can use geometry to find theta A. Right? This becomes a right angle triangle problem, I believe. So I can find theta A. Now, theta A will still not give me theta C. I'm looking for theta C. Okay. Here, so there's an initial position of C, but because of the fact that there's a bit of bending going on, C will have this as its new position. Okay, so let me just take this one out. So now there's a new position of C. So if I draw another tangent passing through C, so I have a tangent passing through C. Let me draw it nicely. Yeah, a point passing through C. What I want to find basically is this angle theta C that makes with the horizontal. Okay. I can't find that yet, but I can find the angle between tangent C and tangent A. So this is theta CA. So I can use a second theorem to find TBA, and then use that to find theta A. No, tangents are tangents. They actually keep going. Tangents don't have a length per se. They just keep going, but because of the way the beam is structured, tangent drawn beyond the length of the beam will not really be useful in any way. All right, so that you don't have to end up drawing a very long tangent. But typically, tangent just keep going, right? They keep going. Okay. I mostly draw them to the side of the beam because of the fact that everything is going to be done within the length of the beam and nothing really outside. So here, I can use TBA to find theta A, which is great. So use Pythagoras theorem. Sorry, the right angle, whatever. Theta A here, and then TBA. Then find that. Great. Now, from inspection, I can also tell that theta A is the same as, so this is theta C is the same as oops. So theta is the same as theta C. I think I've written that already over here. So theta A, which you can find in this case, is equal to theta C plus theta CA. Okay, so if you know theta CA, which you can find using the first theorem, you know theta A, which you're able to find with the help of the second theorem, then here you can make theta C the subject and then find theta C. Okay, so this is the geometry part of it. All right, trying to understand curves. I think it's more of trigonometry, right? Knowing angles, knowing um, opposites, adjacent, hypotenuse, finding theta with respect to the different directions. I think it's more of that, and also maybe understanding these trig principles in terms of the corresponding angles, alternate angles, angles adding up to 180, angles adding up to 90 degrees. Those I think three or four math terms with regards to trig functions. You should be good to go. Okay. So with that, I drew the bending moment diagram for the beam. All right, so this is a bending moment diagram. But what I'm interested in is not just a bending moment diagram, but actually the bending moment over the EI, which is simply the M over EI. So whatever you get for the bending moment, you divide it by the EI. That's all. I mean, the E and I will be given to you, and they are what we call the flexural rigidity. The E is the Young's modulus. The I is the moment of inertia. Okay. I'm sure by now you should be approaching how to find these things in your strength of materials class. Okay. So here I want to find TBA. TBA is the moment of the M over AI diagram. So what do we do? Yeah, so TBA, so the area between A and B. Okay. So with this kind of example, I find it easier breaking them into easy to solve shapes. All right. And the easy to solve shapes are normally the triangles, and then the rectangles. Okay. This has a linear variation. Not all the moments have linear variations. As you can see, if there's a UDL on it, the moment will have a parabolic shape. And if it's a VDL, it will have a cubic shape. And with that one, we'll look at how to solve some of these. Okay. But for now, linear variation, easy peasy. Okay. So I took this triangle and broke them into two parts. Okay. So I have on the left, part one, on the right, two. Okay. So with section one, since this is TBA, it means that I have to take moment about B. Okay. So if I look at region one, the area, so let me just put this on the side. So the area of region one is simply the area of that shaded portion and half base times height. The length here, I think, is what, going back to the problem, that length between A and D is 6 meters. So the length here is 6 meters. The height is 60 over EI. So the area is what? Half base times height. All right. So here you are, half, this is a base of 6 meters times a height of 60 over EI. Okay. Then because it's moments, I need to find the distance, the moment arm from the centroid of this triangle, the left shaded triangle, to B. So I need to find this distance. Okay. And this distance, so let me call it x1 bar. Oops. X1 bar is 1/3 of the length of 6. Okay. Plus this remaining distance, which I think is 2. So plus 2. And that's what I have in this region, 6 over 3 plus 2. Great. Now let's look at the region 2. So with region 2, we know the area 2, again, that is the area of the right-hand shaded triangle. So that'll give us what? Half times a base of 2 times a height of 60 over EI. Again, we have that right here, half times 60 over EI, which is the height, times the base of 2. Okay. And here to your x2 bar, which will be from the centroid of the second triangle to B, that becomes your x bar 2, or x2 bar. So x2 bar is simply 2/3 of the length. So this length over here, and that will be times 2. Okay. So again, we have that in this region. And once we sum the two up, that will give us the TBA, or the T subscript BA, which will be 80 over EI. Okay. If you do your computations, you get 80 over EI. So now we know TBA. So with TBA, did I get my calculations wrong last week? That'll be interesting. Okay. Let me see if I left anything out. Okay, I think I'm good. All right. So once we find TBA, we already know, okay, so going back to our diagram, this is TBA. This entire length, here is 8 meters. I want to find this angle theta. So let's call this, this is theta A. So tan theta A is equal to what? Opposite over adjacent, which is the length. In this case, is 8. Okay. But we know that for very small angles, that angle can be approximated. So for very small angles, we can approximate the tan of that angle to be equal to the angle itself. So that has already been established as an assumption to work with. All right. So it means that theta A is equal to TBA over L. So my TBA is what? 800 over EI. We just found that, divided by L, where L is what? 8. Okay. So it becomes 800 over 8 EI, which is simplified as 100 over EI. Okay, so this is my theta A. Okay. So once I know theta A, I have this equation that theta C is equal to theta A minus theta CA. Okay. So here's my theta A. I just found that one out. It's 800 over 8 EI or 100 over EI. Great. Now I need to find theta CA. Okay. Theta CA, as the first theorem indicates, is the area between point A and point C. That's theta CA. So going oops, okay, I think I went up too much. All right. So the area between C and A is this shaded region. All right, so this is the area between C and A. All right, and have base times height. The base is 2, the height is 20 over EI. So we do these calculations. So right here we find theta CA. Theta CA is 20 over EI. Okay. So 20 over EI for theta CA. We put that into this equation that we've already established. And then from there we can find theta C. Okay. So theta C is giving us 80 over EI. All right. I think we're given the values of E and I. So we can put them into the equation. All right. Make sure that the same units are being used throughout. That is the most important. Okay. So the top portion will mostly be in terms of kilonewtons and then also in terms of meters. So your E should also be in terms of kilonewtons per meter squared. And your I should also be in terms of meter 4. All right. So at least once they all have the same units, then you know that you're on the right path. And whatever answer you get, I mean, writing it in this form is fine, it's great. But usually if there are a lot of zeros before the decimal or after the decimal point, you would want to rewrite it in a more engineering format. Right? And that will be times 10 exponents, multiples of 3. So in this case, it's multiples of 3, which is minus 3. So it becomes 1.11, sorry, times 10 exponent minus 3. And I think you always leave your answers to 3 significant figures. Yeah. So this is the completion of what we were looking at last week. If you have any questions, you could speak over the mic or type it in the spaces provided. Sometimes I believe that maybe talking is easier. So I've been advocating for you guys to go and buy these earphones that come with earphones and mic. Just slots the connector, the jack to the input whatever on the desktop, and then voila, you can speak. It becomes like magic. Okay. So I think that's it for this particular problem. Let's look at something new. I mean, of course, not new, but just let yourself a few more questions. So let's look at, I think, let me put it further. So all the examples I'm trying to solve in the lecture, I've already, there's already a copy of it on the V Campus, right? So you can always go back and review the entire example in its entirety. So let's say you have a beam, okay, a cantilevered beam for that matter. And so let me exaggerate something. So I'm going to draw the size of the beam just to exaggerate the way um, the beam looks like. Normally we use the line method to just do the beam analysis, okay? But what if I have a beam that looks like this? Okay. So my support is right here. Okay. So between A and B, the beam has the size, and then between B and C, it has this other size. Okay. So if I take a cross section between A and B, this is my size of the beam. Okay. So maybe this, let me call this B, let me call this big H. Okay, so this is my size of the beam. If I take another cross section between B and C, this is my size of the beam. Let me make sure that they look about the same. Okay. So the base do have the same B, but then now the H is different, which means that in this case, the H is bigger than small h. All right. So it's the same beam. We have that a lot in structures, right? Where for maybe one length of a beam, the sizes vary along the same beam. All right. So I can have this beam have a load, maybe let's say a load applied at C. Maybe in this case, it's a point moment. I'm pretty sure I might have mentioned this to you guys last time. So we have a point moment, 500 newtons meter, or maybe 0.5 kilonewton meter, depending on how you want to look at it. Okay. So it's the same material, all right, regardless of whether um, excuse me. All right, sorry. So let's say they're made from the same material. Okay. Maybe let's say from structural steel. Okay. So whether it's section A, B, or section B, is the same material, they only have different dimensions, right? So since it's the same material, what is going to happen is that the E is the same, all right? So whether you look at section AB, the E of section AB, so let me call this maybe EAB, and then the E of section BC, the EBC are the same because the same material. Okay. For example, if AB was maybe timber and BC was concrete, then they are different materials. Okay, we do composite design as well as engineers where we combine different materials, different engineering materials together. All right. But in this case, it's the same material. If they were different, it means that the A, assuming that AB, as I was saying, AB is timber and BC is concrete, the E of AB, which is timber, will not be the same as the E of concrete. Okay, it happens. All right. But in this case, there's a material structural steel, so we're good. So the E is 200 GPa for structural steel. Mostly that's what we use in our designs, and it's fine. Okay. The what else I going to say? Okay. I wanted to get onto V Campus yesterday. It wasn't working, but I think it's working, so it's great. Okay. But because they have different sizes or they have different cross sections, it means that the moment of inertia for AB and then the moment of inertia for BC will not be the same. Okay, so it means that along the length of the beam, the moment of inertia will change. Okay. Normally, if you are finding the moment of inertia, again, you come across this. I think moment of inertia with respect to a reference point, it's the same as BH. So this becomes BH cube over 12 plus AD squared. Okay, assuming it's passing through a different point. If it's passing through the centroid, the AD squared goes to 0. Now, IBC will be B small h cube over 12 plus, let me call this one A1. Let me call this one A2. And then maybe this is D1 and D2 because they'll change. All right. So we can see that clearly, I mean, this IAB and IBC would not be the same. Okay. So sometimes you come across situations like that where the cross sections vary. Okay. So if the cross sections vary, then what will you do as what's the name, as the engineer or as the one analyzing the structure to be able to come up with the right answer to solve the problem? All right. See what I want to do. All right. So going through all of this, so with this example, I was given IAB. So that was given the actual value of IAB to be 8 times 10 exponent 6 mm4 and IBC to be equal to 4 times 10 exponent 6 mm4. Okay, I mean, we can see clearly, assuming that I say let IBC be equal to I, then it means that IAB is 2 times I mean, based on the values that we have. I can make this analysis. All right, so IAB is equal to 2 IBC. Okay. I mean, from the whatever I have over here. Okay, because of the ratio. Now we want to find what exactly are we even looking for. Okay, so we should find, I think the question says we should find, so find delta C. Okay, so that's the plan. So step one, you try and draw your elastic curve. Okay. The elastic curve would have to follow the direction of the deflection. Okay. So with this particular beam, it's bending upwards. That if so, let me put here elastic curve. Okay. So if you have the beam, so I'm using the line method to just draw the beam, and I have a load causing an anti-clockwise rotation. About that point, your beam is going to deflect upwards. Okay, so we're going to deflect upwards in this case. So the deflection, whether upwards or downwards, basically is influenced by the direction of your load. Okay. So here, oops, so I have, I think this is my point. So my point B on the curve and my point C on the curve. Point A will still remain where it is because it's other supports. Okay. Now, with this, I need to find delta C. Okay. So what I can do, I can draw a tangent from A. Okay. Thankfully, a tangent from A will be a straight line because A is still on the point. And because this is a fixed support, for a fixed support, there's no rotation at that fixed support. Okay. So this is not, it's supposed to pass through the black point. So let me just, okay, this is fine. So this is the tangent at A. So this vertical deviation from point C to the tangent at A is TCA. Okay. And also the vertical deviation from the tangent at B, sorry, from the point at B. So this vertical deviation here is also TBA. Luckily for us, because of the fact that the tangent drawn from A is horizontal, because it is horizontal, it means that in this special case, TCA is the same as delta C, and then TBA is also the same as delta B. Okay, this is a special case. It's upwards because of the direction of the load, this point moment. All right, it's the deflection is upwards. This point moment is going to cause an upward deflection. Okay, so just assume what's the name? Let's assume that you are holding a beam, and then your left hand is a fixed support, and the right hand side is where you're applying that moment. Okay, so a counterclockwise movement on the right will cause the beam to move upwards, holding the left hand side. So the right hand side is going to move upwards, and by so doing, the deflected shape is an upward deflection. Okay. Again, this is dependent on the loads. Okay. So here we have these two. We can find them. Okay. I won't say easily, but we can find them. So once we have the elastic curve, the next thing will be to draw the bending moment diagram. Okay. So again, let me bring the beam here. I have a moment here, which is 200 Newton meter. The length is what? Did I even put the length there? Okay, I don't think I put the length. So the length here, so again here, LAB and LBC are different. So the length here is, I think this is 4 meters, and this is 3 meters. So the entire length of the beam, so this is 4 meters, and this is 3 meters. Okay, so I need to find these reactions. Okay, and I need to know what these reactions are. Right. I mean, there'll be 3 support reactions. All right. Let me call this. So this is A, B, and C. So I need to find VA, HA, and then MA. Okay. HA is 0. All right. Because you're assuming horizontal forces equals 0. No, the moment is Newton meter. It's Newton meter, not Newton. Oh, what is? I'm sorry. Let me look at what I'm doing. Oh, 500. Sorry. Thank you for the correction. The moment is 500 Newton meter. Yeah, thanks for the correction. Okay. So with that, I can draw my bending moment diagram. All right. You can do the rest. You can find VA, you can find all of that. Okay. VA, I think, will be 0. All right. So summation of vertical forces equals 0. So VA is also 0. All right. If it's some moment about a point, let's say point A, then it means that your MA is the same as the 500 Newton meter. Okay, you can do these things on our own. Please, again, I'm mentioning this to you guys. If for some reason you have challenges with how to draw a Venn diagram, before you have your tutorials, you can get in touch with me or the TS, please. Okay, so my Venn diagram will take the shape. So I have the beam. Okay, and this is a sagging moment, so it's positive. So I have this as my moment diagram. Okay, so each side is 500, so there's a constant. Okay, so this is a moment diagram. It looks quite strange, but this is how they look like. All right. M is positive, and the reason is because of the position of the load on the right hand side C. Yes, most of the time we are used to MA being negative because of the direction of the load, which is downwards, but it is not something that is cast in stone. It's only negative because of the loads. So once the loads change, it's possible that the direction of the moment at A would also change. Okay, so let's take note of that. So we call this point moment. Okay, or some will say concentrated moment. So this is our Benno moment diagram. Okay. It's not exactly what we are looking for. What we want is the M over EI diagram. Okay. So here we know that I think I've established that here is 2I and this is I. Okay. So let me just highlight it because it becomes important to us. Okay. So it means that between, let me just draw a line so that I separate A and B. So on this left side is between A and B, and on the right side is between B and C. Okay. So this is your Benjamin diagram, which is fine. Now I want to divide this by the EI. Okay. So if I take between A and B is 2I, which means that my diagram here between A and B, this becomes 500 over 2I, and that's the same as what? 250 over I. So between A and B, this height here is 250 over I, this height right here. Okay. Then between B and C, it's 500 over EI. Okay. Please take notes. 2I, and then, okay, so let me bring my E here. E is the same, so I think that's like I brought it, I left it. So okay, let me finish this and I'll go over the MA. Okay. So between B and C, there's no change in the I value, so the I is still the same. So it means that here there is an increase. Okay. So this actually becomes your M over EI diagram if you have to take into consideration the effect of the eye. And this discontinuity at B, the discontinuity at B indicates that that is the point whereby there is a change in the cross section of your beam. Okay. So that's something to take a note of. Finding the moment at A. If you sum moment about A to be equal to 0, so so it becomes 500, which is a counterclockwise. So I can make that one positive. So counterclockwise is positive, plus MA, where M is clockwise. Right. So that will be negative. So it becomes plus, so I can say minus MA equals 0. So this becomes the equation that we are looking at. All right. So with this, it means that my MA is equal to 500. It's a moment's calculations. Okay. So let me go over this whole crazy stuff that it looks a bit crazy to us, at least for today. I'm sure after today it won't be crazy anymore. So I think we have established these ones already. 2I and I. I think we should be able to understand. If for some reason you don't get it, you can just quickly text in the space or say something so that at least I can repeat it. And then we can look at it. Okay. So let me just let me call this aside. Okay. So we have a beam. The whole point is that we have a beam, and a beam has different cross sections. All right. It happens a lot in construction. Okay. Sometimes if you have a cobel, um, should I want to give you guys an example of that. Yeah, okay. Sometimes if you have a building, okay, it doesn't happen most of the time, but if you have a building, so maybe these are the floors, okay, and you have the column going through. Usually, the lower you go, the more load you need for the columns, right? So sometimes the columns would have bigger sizes at the base and have smaller sizes at the top. So for the same beam or the same column, let me just use, I mean, the columns, it's not the best way to describe it, but for a particular floor, you can have a smaller size column. And then for the column below, for the floor below, you can end up with a bigger size column. Okay. So if I were to look at this column in totality, this is how it looks like. Okay. So one side has bigger portion, and the other side has one side is small, one side is big. Yes. So going back, so please, when you are finding moments, moments, or when you are finding reactions, all right. So reactions are vertical reactions, horizontal reactions, and then moments if there are. And all of these are found based on directions. All right. Anytime we are summing vertical forces, we have three equilibrium equations. Summing with respect to horizontal distances, summing with respect to vertical directions, and summing with respect to moment about a point. These equilibrium equations can be stipulated or we find them using directions or signs. All right, whether they're going, so for horizontal, is it going towards the left or is it going towards the right? With vertical reactions, is it going downwards? Is it going upwards? With the moment about a point, is it um, against the clock or what's the name? Sorry. Is it against the clock or towards the clock? So is it clockwise or anti-clockwise? All right. That should help you to formulate the equations and then solve for the unknowns. So back here, I have this beam which has different sizes. It's different sizes. So because it has different sizes, it means that its moment of inertia, so let me call this one AB, beam AB, and then beam BC. So the moment of inertia of AB and the moment of inertia of BC will not be the same, because moment of inertia is dependent on the sizes, the shape of the structure or of that particular section. Okay, so here AB is thicker than BC. So because AB is thicker than BC, for the same material, it means that the moment of inertia for AB will be higher than that of BC. Okay. Now, I'm being told that the moment of inertia of AB is 8 times 10 exponent 6 mm4. And then the moment of inertia for BC is 4 times 10 exponent 6 mm4. Okay, we have that. Great. Now I want to write one in terms of the other. Pretty much that's what I'm trying to do. Okay. So if I say, let me call B, C as just I to make things easy for me. So I'm just giving it a notation I, a general moment of inertia. So if the 4 times 10 exponent 6 is equal to I, then it means that the 8 times 10 exponent 6 will be equal to what? 2I. All right. So if I is 4, 2I becomes 2 times 4, and then that'll give us the 8. So it's the same thing that I've done. I've not really done anything crazy, just writing one in terms of the other. Okay. Then I have my bending moment diagram. So I've drawn my bending moment diagram, no different color. So this is my bending moment diagram. It's a positive bending moment diagram. So this is your bending moment diagram. Great. Okay. What we need is the M over EI diagram, not the bending moment diagram. Okay. So it means that we need to divide the values on the ordinates of the moment diagram by their respective EI. So here we got 500 for, so because it's constant, this is also 500 anyway. So every point is 500 on the beam in terms of the bending moments. Okay, so great. So now when I take the M over EI diagram, between A and B, between A, let me just break this down a little bit. Okay. Between A and B, the bending moment diagram divided by its corresponding I. Okay. So pretty much between A and B, my M over AI diagram is actually M over what? EAB and then what? IAB. Okay. So I'm finding the M, the moment between A and B. So this moment here can be constant in this case, or it can be a varying moment, whether it's linear or parabolic. E is the same throughout, so EAB is the same as E. So this is equal to M over E IAB. And here IAB is the same as what? 2I. I don't want to put in the actual value, because when you are dealing with these types of questions, when you put in the actual value of the moment of inertia, which is I think 8 times 10 exponent 6 mm4. See, this is very large. You begin to get very funny answers at the very beginning. It doesn't make it wrong, but then it makes your work a bit more tedious. All right. So, for example, instead of working with 500 over, so let me continue. So this is M over E into bracket 2I. Okay, so that if our M is 500, so it becomes 500 over what? E into bracket 2I, which is the same as what? 250 over EI. Okay, this is a much more conservative way or better way to write it. The other option which I found student doing is that, okay, the M is E, sorry, oops.
Yeah, hello, sir. Sorry to cut you off. Okay, the power just went out.
Power. So,
yeah.
So your screen is off, right?
Yes.
Yikes. Okay, we'll see what we can do if I have to. Most of us should still be seeing it on our lap. Okay, we are started going off already. Oh, this is interesting. Okay. So what should we do? We should pause.
What I am suggesting is that I believe some of them do have their phones with us. So just
All right, so let me go ahead and continue with what we were looking at. Try and wrap up the question. A moment. Yeah, so as I was saying, sometimes you can go about this approach where you actually put in the values of the M over EI. So in this case, since it's M over E IAB, then this becomes 500 over E, 8 times 10 exponent 6. So let's convert it to meter 4. All right. But you'll see that this becomes very small values when you are done with the computations, and it makes calculations extremely difficult. So I would not advise this. Okay. Or you can also get very large values. So in this case, we are converting everything to meters. You can usually get very large values. You don't want to work with all of these. So I would advise that we just, if where possible, if you can write the moments of inertia of the different sections in terms of each other, it makes our computations easier. Okay. So here we'll see that the IAB here, because it's 2I, then this will reduce the M over EI between A and B further, all right? And then for the BC, again, so this is for BC, this side becomes M. Let me just write it down here so that they follow. This one becomes M over E IBC. Okay, so M over E, since IBC is the same as I per what we were looking at, so this still becomes 500 over EI. Okay, so we can see that this is more or less, so this has, it looks like it's higher, or there's not be any change in the moment, the M over EI diagram. Okay, so we'd end up with this kind of like joints or the shape, right, where there's a change in the cross section. Okay, so once we have the shape, then it's easier to now work with it. Again, the goal was to find T, was to find T B, sorry, I think TCA, which in this case is the same as delta C. So TCA, which is the moments of the M over EI diagram. Okay. So that will give us, so I can look at the smaller section and the bigger section separately. So the area is, this is 250 over EI times 4. So here the base is 4. So I'm just finding the area. The base is 4. And then the moment arm, so it's with respect to C. All right. So the moment arm will be, so this is the centroid. So this distance from the centroid to B, where to C, sorry. So this is C. It's to C. So from that to C would be half of the length, which is 4/2 plus 3. Okay. Then the right portion would also, let me just take this guy away so that I can have space for that. So the right portion, this was here. So the right portion will be, so this height is 500. I didn't put it there earlier. So 500 over EI. So it becomes 500 over EI times, again, the base here is 3. So times 3. And then the moment arm would be half of the 3, which is 3/2. So it means that your TCA would be so I think if you add everything, you get 7,250 over EI. Okay. But please take a note, this 7,250 is a Newton meter. Okay, because of the fact that we have our what's the name? Our moment in Newton meter, right? Maybe in not to confuse you, some other or subsequently you can actually make sure that your moment is in kilonewton meter before you do any calculations if you want to make things easier. Or I mean to have some kind of like consistency so that things don't get messed up along the line. Okay. So this is 7,250, which is a Newton meter. So I'm converting my E also to Newton per meter squared. So that'll be 200 times 10 exponent. Oops, my screen is messing up. Oops, okay. 10 exponent 9. And this will be in Newton per meter squared. Okay. Then hopefully I have enough space to write this. I doubt. Then the I, since here, this I is supposed to be the IBC, and that is the 8. If you convert, it becomes 8 times 10 exponent 6, sorry, minus 6. Let me move this ones a little bit to the right so that I can have enough space. Okay, great. So it becomes, let me just rewrite it. 8 times 10 exponent minus 6. And this, the unit will be in meter 4. So once we have all of that, it means that my TCA, okay, so TCA, again, the same as delta C anyways, in this particular scenario, so we're good. This will end up with getting 0.0906 meters, okay, which is the same as 9.06 millimeters. So the same way we found the TCA, we can also find TBA. Okay. So TBA, the same as delta B. Okay. So again, that'll be the moment of the M over AI diagram between B and A. So that going back here, that would just be this left side. Okay. We will not include the right hand side because we are finding the moment of the M over AI diagram between A and B. Okay, so here we have A here and we have B there. Okay. So the area of that portion will be 250 over EI times the height of 4, right? It's like a rectangle. And then the moment arm from the center of the rectangle to B will be 4 over 2. So that will give us 2000 over EI. Again, the I over here is actually IBC. Okay. And IBC is, if you convert it into meter 4, then it becomes let me make sure I get it. Sorry, please. Going back here, the IBC is not 8, IBC is 4, sorry. So let me check this one. The IBC is 4, please take note. The IBC is 4, okay, not 8. So if you convert the IBC, becomes 4 times 10 exponent minus 6 millimeter exponent 4. Sorry, meter exponent 4. Again, take a note, this is in terms of newtons a meter. I think the actual thing is Newton meter cube, right? If you want to look at it properly. And then E2 should be written in terms of Newton per meter squared. Okay. So if you do that, we should end up with 0.0025 meters, which is the same as 0.0 so let me see 0. As long as my screen is writing, has been happening of late. I need to figure out what the problem is. So this should give us 2.5 millimeters. All right. Okay. Now there are a few things for us to take notes. Let me just bring them into view to help us. And just move them up here a little bit. And then maybe they just go up a little bit more. Okay, so there's some aside information, okay, as to how to find area and also find the moment arm. Okay, so for a rectangle, let me just extra information on geometry. So for a rectangle, so that is like moment, right? So I'm looking at moment diagrams. So for a rectangle, this is the area. So we have the height, we have the base. So the base is B, the height is H, so the area is B times H. Okay. Then the moment either to the left or right will be half of the base, okay, which is B over 2, because the center of gravity is right at the midpoint or at the center of the beam. Okay. Then in the case of a triangle, okay, a triangle, the area of a triangle is half base times height. Okay. So that will be here, our base times height. We know our height, H, our base will be B. So half of that area will be half base times height. Now, if the centroid or the center of gravity, okay, it's not at the center of the structure, it's not here. Nope. Okay, it's not at that center. It's skewed towards the end with the height. Okay, it's towards the end with the height. All right. So to find the moment arm from the center of gravity of the of the triangle towards the right. So let me call this point maybe K towards K. And that distance x1 bar will be 2/3 the length of the base. Okay. So for example, if the base is maybe let's say 9 meters, that means that x1 bar will be 2/3 times 9. And that will give us an x1 bar of 6. All right, 6 meters. Okay, so that is towards the right. Now, if it's towards the left, then your x2 bar is 1/3 times the base, which again is 9 meters, assuming it's 9. So this will give us x2 bar of what? 3 meters. Okay. So that's something to take note of. Then, so these are usually for cases whereby the loads are either rectangular, sorry, the moments are either rectangular or the moments are triangular. We can also have cases where moments are what's the name? Parabolic. All right. So they can be either in a concave shape, all right, or in a convex shape, depending on how the structure looks like. So for the convex shape, and this is the concave. So the convex shape is area 1, and then the concave is area 1, and the convex is area 2. All right. So for the concave, the area of the concave, that's the one with the 1 in there, is 2/3 times the base times the height. Okay. And then the moment arm from the center of that area 1, which is what I have over here. So from the centroid of area 1 towards the right hand side, I call that one x1 bar. Okay. And x1 bar is it's 3/8 times the base. Okay. So for example, again, assuming that we have a base which is equal to 9 meters, then x1 bar is 3/8 times 9. All right. And then that will give us some answer. You can also have, so maybe I could call, so if this one is x1 bar, then maybe towards the left, I could also have maybe, let's say, x1 dot. Okay. So towards the left, x1 dot will be 5/8 times b. Okay. Just take a note of it. Now, when it comes to the convex, which is area 2, the area is 1/3 base times height. Okay. So 1/3 base times height. And from the centroid of B to, let's say, the right-hand side, which again is like naming it point K, that becomes so that will be this distance here, which I call the x2 bar. So this distance here, let me just reduce the size. So this is x2 bar. Okay, and then we can also have one from the centroid. This is the centroid towards the left-hand side. Maybe I can call it x. X2 dots. Okay. So x2 bar is 3/4 times b, and then x2 dots is equal to 1/4 times b. So these are some geometry information that could be helpful to us going forward. Okay. Now let's look at some examples, some ones that will be of use to us. And I'll call them special. I won't call them special cases per se, but there are certain beams. Let me just bring this one up. I drew them earlier. Let me just bring them up here. Okay, another one on the right. Great. Okay. So this will be the elastic curve. So we have here the elastic curve. Okay. All right. So when you look at the elastic curve and there, so let's say we have different points on the elastic curve which are important to us. Okay, so all these points, we can find the tangents to these points. Let me just exaggerate a little bit. So I can try to have a tangent here and that tangent. So we can have tangent passing through as many points as possible. And we can see that as we keep drawing the tangents, you would realize something interesting. At some point, one of the tangents is horizontal. Okay. At some point along the elastic curve, one of the tangents would end up being a horizontal line. Okay. Which means that if that happens, then that slope, sorry, not C, that slope at that unknown tangent, so let me use the letter K, for that unknown tangent is 0. So if we can find that particular point for these types of curves where the slope is 0, that would also give us the maximum deflection at that point. So somewhere between A and B, there is a point on the elastic curve. So let me say somewhere between span AB, there is a point on the elastic curve whereby the tangent drawn to that curve is horizontal. Okay, so this means that the slope is 0 or the angle of rotation is 0. Okay, and when that happens, it means that you would end up with the case whereby we can find our maximum deflection. All right, so let's look at this. Okay, so in the case of a simply supported beam where the loading is symmetrical, I mean, or the load is at the center point, normally for these cases, you would realize that your maximum deflection would occur under the load. In this case, please. Okay. So maximum deflection occurs at C. Okay. In this case, please. Let me put here in this case. Okay. It's not always the case, please. So that you know, use that information everywhere you go. Okay. Empty. So going back, let me just delete these guys. I don't think I'll need them. Let me just delete you so that I don't end up with the same thing. Okay, great. So now let me draw the elastic curve and then bring, I think I have it already drawn. Let me just copy it and bring it, show it to you guys. Okay, so here I have the elastic curve. Let me make sure that it looks nice. Oops. Um, okay, I'm just trying to increase the sizes of some of the parameters so that they look nice to see. Okay. So here I have tangents drawn from A, B, and C. Okay. So here is a tangent from B, and then here is a tangent from, oops. Okay, now this looks better. Okay. So the tangent drawn from A is shown in this highlight. So the yellow highlight. The tangent drawn from B is shown in this other highlight. Why is it not showing? Okay, whatever be the case. Okay, it changes depending on which direction we are looking at. Okay, I think I made it smaller. Okay, great. So the tangents, all right. And then, so if this is point A, this is point A, this is point C on the elastic curve, this is a point B on the elastic curve, okay? The vertical deviation from point A to the tangent drawn from B is given as TAB, okay? And then the vertical deviation from point B with respect to the tangent drawn from A becomes TB. Okay. Now, at tangent C or at point C on the elastic curve, its tangent is a horizontal line because that's the point at where what's the name? Deflection is maximum or slope is 0. Okay. So it means that the theta dx is 0 at that point. Okay. So these are some other parameters which are of use to us. The vertical deviation from A with respect to the tangent drawn from C, this distance here, that distance here becomes TAC. So we have it here, TAC. And the same way too, if we take the vertical deviation from point B with respect to the tangent at C, then that would also be TBC. Let me rewrite that here. So this will be, so this here will be TBC. Then we also have, so this is C. Okay, so this is C on the elastic curve. So the vertical deviation from C, let me write it closer to the point. So from C to any of these lines, okay? So this vertical deviation here is TCA with respect to tangent A, and also the same as TCB, because this point is where both B and C interact. Okay. Now this angle, the angle between B and A is theta BA, sorry. So it's theta BA. Okay. And the angle between C and A, this angle is theta CA. And then the angle between B and C, this angle, it can be either here or there, it's fine. It's theta BC. Sorry, yeah, theta BC. Okay. So we have all of this information, okay? Just the key thing will be how to draw some of these things, okay? And then once we have that, we can compute for whatever we are supposed to, okay? So here again, it becomes a trigonometry problem. I can look at it this way. Let me have this showing. Let me use a different color. So this is line AB, I have the tangent drawn from A. So this is tangent drawn from A. I have this vertical distance here, which is TBA, the vertical deviation. This is point C somewhere and there. So I have this distance, this entire distance. A portion of it is delta C, another portion of it is TCA. All right. So let me call this, and so this whole height here, let me use a different color, this entire height. Okay. Let me call it T prime. So that T prime is equal to delta C plus TCA. TCA. All right. So that's the whole idea. This is L over 2. This is also L over 2. Okay. The angle here will be theta A. Okay. So using the principle of similar triangles. So here using similar triangles, we can say that T prime will be equal to TBA over 2. So the height T prime will be the same as half the height TBA. All right, similar triangles. Okay. Which means that if we want to find delta C, that means that here delta C will be equal to T prime minus TCA. Okay. Where T prime is TBA over 2 minus TCA. Okay. So we can find TBA, we can find TCA, and once we find that, once we're able to solve for these two parameters, then it means that we can find what's the name? Once we do that, we can find what's the word? We can find the delta C. Right. Sometimes to make your calculations maybe less tedious, okay, we at least from this, either way doesn't really matter. It's fine. Let me just not say that so that we don't get confused. All right, so we can find these parameters. We can find all of them. And then we can find delta C. Okay. The other way to look at it, so we can use this, let me call this approach 1. This is approach 1. The other way to look at it would be, again, back to the beam, then back to our curve. Okay, yeah. And then we have these tangents drawn from A, and then the tangent drawn from C. Okay. So this is tangent drawn from C. This is tangent drawn from A. Okay. So this is your point A, this is your point C. Okay. This vertical deviation is TAC. We also want to find this height here, delta C, right? So because tan C is horizontal, which means that the slope at C is 0, then it means that for the approach A is more like a general case, right? Regardless of what the orientation of your slope would be at C. But for the second approach, which is approach 2, we are using approach 2 based on these assumptions or these conditions. That the tangent axis is horizontal. We are fully aware that the tangent axis is horizontal. The slope axis is 0, so that gives us a horizontal tangent. And for that reason, we can say that, okay, TAC is the same as delta C. So it means that if I find the vertical deviation of point A with respect to the tangent drawn from C, then that becomes delta C. All right. In this case, delta C is the same as the maximum deflection delta max. Okay. So approach 1 is a general approach, and approach 2, I'll call it the specific approach. Okay. So in all of these, we need to draw a bending moment diagram, okay, which is one of the first things that we should have done earlier. So a bending moment diagram will take this shape, okay, where the maximum is PL over 4. Okay. So there's a bending moment diagram. If you want our M over EI diagram, we just divide that, assuming that in this case, our M and EI are constant. So our plot remains the same, but now it becomes PL over 4 EI. So this becomes our M over EI diagram. Okay. They look about the same, but they are actually different in the sense that one we are dividing the moment by the flexural rigidity. Okay. So this looks a bit off. Let me just make sure. Okay. So this is point A. C is here, and this is B. Okay. This is supposed to be an isosceles triangle, right? So isosceles triangle, or maybe it could also be equilateral, assuming they all have the same sides. Equilateral. Okay, great. If it's isosceles triangle or equilateral, whereby these two sides are the same, then what it means is that for this special case, so become a special case triangle, your centroid is right at the center of the diagram. Okay, so your center of gravity is right at the center of the diagram, which means that your X bar here will be half the length, which will become L over 2. Okay, so just take a note. So this is a special case, all right. So once we have that, the next thing will be to find, so let's say we are finding these parameters TBA and TCA and all of that, okay. So TBA will be equal to the area of the triangle, right? So that's half times the length times PL over 4EI. Okay. And then times the moment arm. So we are taking moment about B, that is L over 2. Okay. So times L over 2. And this should give us PL cubed over 16EI. All right. So now we have TBA. Now let's find TCA. So with TCA, our focus will be trying to look at this portion, okay, with summation of moment about C. Um, So I can just redraw this. Oops. Just redraw that over here like that. Okay. Terribly drawn. So I need to, so we're taking moment about C. So I need to find this length here. And this length is what? 1/3 of the base. Okay, we have established that this is the base. So here my base is supposed to be L over 2. So it becomes 1/3 of the base, and this is 1/3 of L over 2, which is actually L over 6. Okay. So TCA is half. Oops. Okay, and the screen is messed up again. Okay, this is great. It's back. So 1 over 2 L over 2, which is the base, times the height, which is PL over 4EI, times the moment arm, which is L over 6. Okay. And this should give us PL cubed over 96EI. So it means that our delta C here is half of the TBA. We have, let me just take that information. Okay, let me just write it here. So half of TBA minus TCA. Okay, so this becomes half of PL cubed over 16EI plus PL cubed over 96EI minus, not plus, minus. Okay, so this will give us PL cubed over 48EI. Okay, so please note this becomes our maximum deflection as well. Okay, so this occurs where the rotation is 0 along the length of the beam. So this is approach A, which is all well and good for approach 1. For approach 2, what is approach 2? For approach 2, we are saying that TCA is equal to delta C. Right. So again, so this is approach 2. Again, I'm looking at TCA, so I'm looking at this portion. All right. But because I'm doing TCA, is it TCA? No, TAC. Because I'm doing TAC, which is same as delta C in this case, it means that I need to find the moment. So my X bar would be with respect to about A. Okay, so take note of that. And this is PL over 4EI. So TAC will be equal to half. The base is L over 2. The height is PL over 4EI. Here, your X bar is 2/3 of B. Okay. Again, B is L over 2, so it becomes 2 over 3 times L over 2, and that'll give us L over 3. So here becomes L over 3. Okay, and then or maybe let me put in the general term so that we know what we are doing, like this, and that will give us PL cubed over 48EI. All right, so they both are the same. Okay. So the options, one is a general approach which would work for the different sections. All right, as compared to approach 2, which is specific for the case that the slope at C is 0. Sorry, yeah, the slope at C is 0, which also means that that will give us the deflection at, what's the name? The deflection at C being the maximum deflection. Okay. So here, going back, we can also find the other data that we need. So we can find theta A. We can also find theta B and all of that. Okay. We can do that and find their respective rotations at the different points. Okay. So let's summarize what we've been looking at. So in summary, so when you are given these types of problem, one, you try to draw the M over EI diagram. Okay. So take note of the E and I values if different. Okay. Then two, you draw the elastic curve. So you draw the elastic curve and you indicate pretty much some of the tangents and all of that. Okay. And by doing that, we should be able to identify um, identify the deviations and the slopes between points. Okay. Then from there, the fourth one will be to calculate the actual deflections. So then let me see the actual deflections, and then slopes, where these slopes are respect to the horizontal. Okay. So depending on what you are being asked to find, we should be able to do that. Okay. So this is the summary for us. Let's have that in mind. So the example that we solved above, we made some assumptions, right? The load is acting right in at the midpoint. So because the load is acting at the midpoint and the support conditions are also simply supported, or I mean, the conditions have to be the same on both ends. Our deflector shape like this. Okay. So the maximum, the deflection, let me call this C again. The deflection at C, delta C in this case, is the same as the maximum deflection. Great. Now when you come, so I can draw the same structure. All right, and let me draw with the same length. Okay. Then again with the same boundary conditions. But in this case, I have the load. Let me change the color to red. So now I have the load to the right, P. All right. So my diagram will look like this. Now this point C, yes, is the midpoint, all right. But in this case, the deflection at C, delta C, would not be the maximum deflection. Okay. The maximum deflection is likely to occur closer to the load. Okay. So let's say if this is L over 2, and here is also L over 2, great. Maybe I can make this whole length here, maybe 2L over 3, and make this length here L over 3, just to show the difference in the length. All right. So delta C, in this case, will not be considered delta max. And the reason is that in case 1, so this is case 1, this is case 2. In case 1, your slope at C is 0. Right, but just in case 2, your slope at C is not equal to 0. All right. So there are a few things that would determine how these things occur, which means that finding your maximum deflection depends on the location of your load, or the load positions. Okay. It also depends on the flexural rigidity, flexural. Okay, which will be the E and I. Okay. Mostly is the I, because the E usually is constant. That's the Young's modulus, or the modulus of elasticity, which is usually constant. We don't really try to change the materials. But for the same material, we can change what's the name? We can change its cross section. Okay. So let's see. I think this should bring us to the end of today's lecture. So next week we'll look at the conjugate beam method. Okay. So we can look at that next week, and then hopefully we can also solve some examples, understand how it works, and we'll see how it goes. All right. So I'll end the recording here, and yeah, I think that's about it for today. All right. So we'll meet again next week, and let's be available for the tutorials, I think next week, Thursday or so. All right. Bye.